Okay, now we're back for the derivation of the ratio of Wronskian form of the solutions for the V1 and V2 in the variation of parameters method. So given x of h equals c1 x1 plus c2 x2, we assume that xp equals v1 of t x1 of t, of course, plus v2 of t x2 of t. Now, what does that mean? Well, that means that these component functions satisfy x double prime plus p of tx prime plus q of tx equal to 0, and our full particular solution satisfies x double prime plus p of tx prime plus q of tx equals f of t. So that's what we mean when we say this is the homogeneous solution, this is the particular solution. Two different forms of the equation that they solve. So now we want to take derivatives of our xp, just like with the undetermined coefficients method. We're going to plug it in. We're going to plug it in. So first we compute xp prime. And I'm going to drop the of t for each of these because everything's a function of t. P is a function of t, v, x, q, f, they're all functions of t. So I'll just write the letters to represent them. The derivative of xp has product rules. So we differentiate the v1 first, v1 prime, x1, and then the x1 differentiated. So there's our product rule for the first product. And then we add v2 prime x2 plus v2 x2 prime. And then before we move on to the second derivative, let's just pause for a second. First off, this is going to get crazy. It's going to get out of hand. So for our own sanity, we need to make some simplifications. But we want to do it in a way that allows us to only find one form of each of the helper functions, v1 and v2. To do that, we want to avoid having any kind of v1 double prime or v2 double prime, because second derivatives involve two solutions, two linearly independent solutions. So we want to keep the v's from getting to a second derivative. To do so, think of this as v1 prime x1 plus v2 prime x2 plus v1 x1 prime plus v2 x2 prime. We're going to group them like this. These are the terms that we're fine with because taking derivative will only lead to a prime first derivative on v1 and v2. These are the terms that we're not okay with. So we're going to force the terms that we're not okay with taking derivative of, force them to 0. So we're not forcing any particular one of these pieces to 0, we're forcing the sum together to create one function. Force to 0 to simplify. I mentioned before that we're only trying to find one, we're only trying to choose one helper function for each of the x's, each of the homogeneous pieces. So we need to make some simplification, and this is a really helpful simplification. So that means our xp prime is actually just v1 x1 prime plus v2 x2 2 prime. And we'll have to come back to that condition a little bit later. Now we can take a second derivative, and we'll be fine having only first derivatives on the v1s. So v1 prime x1 prime plus v1 x1 double prime, v2 prime x2 prime plus v2 x2 double prime. Okay. Now we look at the pieces we have, xp double prime, xp prime, and xp, and we want to plug all the pieces in to our equation. To do that, I'm going to look at how each component adds in. So I have xp double prime plus p xp prime plus q xp equals f of t. Now, again, that's a function of t. Everything's a function of t here. Everything's a function of t. So I'm first going to write this in terms of the v1 terms. So from all these pieces, I'm going to check to see which are the terms that are multiplied by v1. So I look over and I say, here I have an x1 double prime. And if I go up to xp, there I have a plus p times, maybe it's just helpful having the functions of t there. I'll put them back. Okay, I'll put them back. P of t times v1 x1 prime, and then going up to the top, I have a v1 x1, so plus q of t times from the xp term, I have a v1 times x1. And then I add the v2 terms. Starting at the bottom again, I have a v2 times x2 double prime. Then I move on to my xp prime. I multiply by p of t, and I have a v2 x2 prime, and then going to the very top, I have v2 x2. So plus q of t times xp gives me a v2 times x2. Okay, so I have the v1 terms, the v2 terms. Now I go into the v1 prime terms. And I check. Here I just have one piece, that's x1 prime. I look up. No, because I can force that to 0. That was from the second one. So that's the only term for v1 prime. And then for v2 prime, I'm multiplying by x2 prime. And that's the only term left. And all of this together equals f of t. Okay, so that's a lot. But there's some simplifications we can use. One, we have x1 double prime plus p of t x1 prime plus q of t x1. That is the same derivative pattern, only on x1. And we know that x1 is one of the homogeneous solutions, so it satisfies x double prime plus p of t x prime plus q of t x equals 0. So this full piece, this first chunk, is all 0. And the second chunk is the same thing for x2, and x2 is also a piece of the homogeneous solution. So x2 also, so this whole second chunk also equals 0. And that means that we only have two pieces added together and are remaining equal to f of t. So that gives us let's see, v1 prime x1 prime plus v2 prime x2 prime equals f of t. So that is the remaining condition we have from plugging in our equation. And this is written in terms of the derivative of the two unknowns, v1, v2 prime, multiplied by x1 prime and x2 prime. But we know x1 and x2, assuming that we're given the solution. So we have one equation and two unknown. Oh, wait a second. We actually have two equations because we have this condition we forced over here. We have v1 prime x1 plus v2 prime x2 equals 0. So now we have two equations, both of which relate the derivatives of v1 and v2 and are connected to x1 and x2. So now we need to put them together and solve that linear system. So let me clean the board a little bit so we can write this linear system and solve it. So, given our homogeneous solution and assuming that xp is equal to this functional multiple or functional combination of x1 and x2, then v1 of t and v2 of t satisfy x1 v1 prime plus x2 v2 prime equal to 0, and x1 prime v1 prime plus x2 prime v2 prime equal to f of t. Now, why do I write them in that order? Well, if you notice the pattern, there's x1 and x2 and x1 prime and x2 prime. That pattern forms our Wronskian. In fact, we can write this in matrix form as x1, x2, x1 prime, x2 prime multiplied by v1 prime, v2 prime equaling 0 f of t, where the Wronskian of x1 and x2 equals the determinant of this matrix, x1, x2, x1 prime, x2 prime. Now, how do we solve this linear system? Well, we could no, we don't want to reproduce. We can use Cramer's rule. Why? Because we know this Wronskian is non-zero, because our x1 and x2 come from linearly independent solutions in the homogeneous solution space. So by Cramer's rule, since Wronskian x1, x2 is not equal to 0, v1 prime is equal to the ratio of the two determinants, where the bottom determinant is the Wronskian, and the top determinant is that Wronskian modified by the right-hand side, 0 f of t, keeping x2 and x2 prime. So that is the derivative. Well, to get to the function, we simply integrate the derivative, and we get v1 is equal to the integral of our w1 divided by w dt, where w1 is the modified Wronskian, placing over the right first column, and the Wronskian of x1 and x2 is written in shorthand as just w. In a similar way, v2 prime is equal to the ratio of the two determinants, where the bottom determinant is the Wronskian, the top determinant is that same determinant, but with 0 and f of t modifying or pasting over the right-hand side, or the second column, x1, x1 prime. And so, again, by integration, we undo our derivative on v2 prime, and we get the form of our solution, v2 is equal to the integral of w2 over w dt. So there we go. That's the derivation for how we form the v1 and v2 by the integral of the ratio of two determinants, because they satisfy both the condition we placed upon them to simplify to a single first-order differential equation, and then finally the resultant equation after we plugged in what the homogeneous functions meant in terms of what things canceled out. So those two equations that they satisfy then allow us to solve for the two unknowns, and we pick up pieces of the known functions x1 and x2 in the form that matches our Wronskian, which proves that we can solve it using Cramer's rule because there's a unique solution. And there we have it. Okay. Now, we'll head back and do some more examples of class.